The basic idea with sample rate conversion is that there are lots of situations in which you have a discrete time signal. Maybe it was acquired by sampling at a certain rate, and you would like to convert that to a set of samples that would correspond to having sampled at a different rate. And so it's essentially changing from one sampling rate to another. And other contexts in which you might want to do sample rate conversion is for data interpolation. Whether or not the data inherently has an underlying continuous time signal associated with it, it may be that you want to zoom in on the data. For example, if you had a signal that you thought was sinusoidal, or data that looked like it had an oscillating trend to it, and you wanted to eyeball what the amplitude was or what the frequency of that is, just having samples, 2+ samples per cycle, looking at that data, it would be very hard to infer what the amplitude or frequency or phase of that periodic trend might be. Now, 2+ samples per cycle is fast enough to, according to Nyquist, recover or infer what the underlying sinusoidal trend is, but that doesn't mean that by eye you'd be able to do that interpolation. So very often, when you're looking at data, what you want to do is upsample it, whether or not that data inherently corresponded to sampling a continuous time signal. Other contexts are, for example, in audio systems, in other kinds of systems, there are various different standards that are used for the sampling rate. So in audio, for example, one standard is 44.1 kilohertz that you would sample at. Another standard is 48 kilohertz that you would sample at. And if you have data sampled at one sample rate, but you want to combine it with data at another sampling rate, obviously you have to make the sampling rates compatible. So that's the basic idea of sample rate conversion. And one obvious way of doing sample rate conversion is by taking the data and going through a D to C converter and then resampling at the new rate. The main point of today's lecture, actually there are two kind of main points to today's lecture. One has to do with how you would do this, but directly in the discrete time domain. Another has to do with the fact that there is upsampling and downsampling that can be exploited in a very sophisticated way and a very important way in the context of implementing discrete time systems. And so, and that's referred to as, eventually we'll be referring to that as polyphase decomposition. And in today's lecture, we will just take one step in that direction. So before I get into doing this, though, I want to mention also, and this will come up more in Tuesday's lecture, that one of the common uses of sample rate conversion is in A to D and D to A conversion. And for example, in essentially all compact disc players, CD players, and other kinds of musical storage or audio storage, it's very common to use what's called a 1-bit DAC for the digital analog conversion and 1-bit quantization for the A to D conversion. And something that's inherent in doing that is the use of what's referred to as oversampling. So in the next lecture, I'll be talking about quantization, oversampling, and what's the way it's typically done, which is referred to as oversampled noise shaping. But if you look at most modern A to D and D to A converters now, they tend to utilize bit streams or one-bit quantization. And what lets you get away with that is by incorporating a very high degree of oversampling. So this is a fairly generic block diagram. It's actually a block diagram for a particular chip that was manufactured by Analog Devices. But I just kind of want to draw your attention to a couple of blocks here. So typical A to D conversion now involves what's called sigma delta modulation. And I'll be saying something about that in Tuesday's lecture. And it involves a very high degree of oversampling on the analog signal, followed by some processing and then decimation, in other words, downsampling. And then in the D to A conversion process, there's exactly the reverse, which is to take the one-bit digital data, interpolate it, and then come out through a one-bit D to A converter to the output. So oversampling tends to happen in the A to D conversion stage, followed by what's referred to as decimation. In the D to A conversion stage, it's interpolation or upsampling, and then followed by requantization so that the actual D to A conversion happens just on a bit stream rather than on a more complicated coding of the signal.